1.5 ton. Now we can write them up a quote for that. Okay. Alright guys, so you didn't feel like watching that last video because it was ungodly long, but there was a lot of good information there and I hope you go back and look at it. Anyway, we are going to actually take a little bit closer of a dive into this apartment that we're working on, that we're doing a load calculation and HVAC design for. If you go back in my videos, you'll see the apartment that we're actually working on. But anyway, so what you're going to need to do here is you're going to have to grab your blueprints or whatever notes that you got on your site visit, a calculator, maybe pen and paper, and of course your book. So what I've decided to do here, because I'm not trying to endorse anybody's program or anybody's software, our other options would be, okay, well then we're gonna have to do this pen and paper. We're gonna have to get a pen and paper, we're gonna have to go through everything, figure everything out, do a lot of math. What I've decided to do is kind of meet you in the middle, okay? We could do pen and paper, or we could buy a several $1,000 software. We're not going to do either one of those. We are going to actually go and work with ACCA's speed sheet for their manual JAG. Now this speed sheet, the one that I've had here on this computer, I've had it for probably 15 years or better. And I don't know if there's something that has been updated through ACCA is in regard to their speed sheet. I don't even know if this is still available. I'm assuming it still is, but again, I don't know. But anyway, it's kind of the middle of the road because it's more or less a glorified Excel spreadsheet that we are going to be inputting some information in, and it already has a few formulas built into it to where it will spit you out a few numbers associated with your heating and cooling loads. So that is what we're going to work on today. I'm going to get this thing loaded up and I'm going to throw it up here in the screen so you can see what I'm doing on the computer. Okay, we have our speed sheet up from ACCA. Now, I'm going to walk you down through this whole thing really quick. I want to keep this video as brief as possible. So, what we've got here is our Excel spreadsheet, essentially. Every box that you see in here, they're all color-coded. Okay, the green stuff, they're just labeling different columns. The white boxes are areas that you are physically going to be putting some sort of data into, okay? Whether it's a name of a room or the state, city you're working in, the area, like dimensions of windows and doors, that'll all be going into these white areas that you see on this screen. The blue areas, those are nothing that you are directly going to be putting information into. What it is the spreadsheet is actually calculating something for you, and it will automatically formulate some data and put it into those boxes, so you don't have to worry about those. And then the yellow boxes that you see on the left-hand side there, those are going to, once we start putting some data into the spreadsheet on these other pages, these are drop-down boxes that you will use to, tell the formula what material you are working with. Like I said, all these white areas, that's where we are going to be putting some information into them. Let's start at the very top left, and we've got a tab that says project, okay? So we've got to put something in here. I'm going to call this apartment 1. That is going to be the name of this project. Now, we go to our design, state, and city. Where are we working? Anybody? No? I'm just going to pick one here. Let's say we're working in Alabama, okay? I have never been to Alabama. I don't know anything about Alabama, but we are going to pick a city in Alabama, and I'm going to pick Auburn. Again, I don't know anything about Alabama. I don't know anything about Auburn. I don't know where it's at, but that's what we're going to say that we're building a house, okay? Or this apartment has lifted itself up and landed in Auburn, Alabama. So you can see that the spreadsheet is automatically starting to input some data in here. Directly below Alabama, you can see that we've got our outdoor 99-degree dry bulb, or 99% dry bulb temperature, 22 degrees. Okay, so that is what we are going to be sizing our heating system on. Directly below that, we've got our outdoor 1% dry bulb, which is what we are going to be sizing our air conditioner on, 93 degrees. We're not going to be sizing it for 105 because I'm sure that it gets in excess of 100 degrees in Alabama. As a matter of fact, it might be hotter than 100 degrees there today. I mean, it's right now, it's the beginning of August. We are seeing a heat wave here. I'm sure Alabama is toasty. So we are going to size our air conditioner for 93 degrees in Auburn, Alabama. So below that, we've got our grains difference. If you look back here at our psychrometric chart, I know you can't see it because there's a glare, but we've got all of our grains per pound and that's what we're working with here. It's all automatically given us our elevation that we are designing everything to. We go to the next column over here. We have our heating temperature design difference. That's 48 degrees, which is actually not bad. That's pretty low. But again, this is Alabama, so I would expect a lower number there. And our cooling temperature difference, 18 degrees, kind of what I would expect. We have our daily range, medium. So again, if you remember in the last video, I talked about our daily range in our table 1A of the Manual J book. That kind of, you either have a low, medium, or high for that particular thing there. Then we've got a medium, and then we have our ratio between heating and cooling equipment, and we're at a 0.9. So like I said, once you get closer to that 1, kind of gives you the assumption that you have a relatively even heating and cooling load throughout the year. So this would be a prime candidate for a heat pump maybe. Okay, let's take a look at this though. If we go all the way back over here to the left where we've got our design indoor heating drybulb and our indoor design cooling, these are again white boxes that we can change. Okay, we can change the data in these boxes. This is a default setting to where 70 for heating, 75 for cooling, 50%. I mean, that's a pretty comfortable condition. Now, if you wanted, after having a conversation with the homeowner, they said that, they want their heating to be 75 degrees, then you can put that here. You can simply put, 75 degrees and boom, there you are. Now it's going to be calculating all of our heating loads on a 75 degree indoor temperature. For cooling, you talked to Jim, the owner here, and you said, hey, you know what? I want to hang meat in my living room, and that's what I want to do. That's fine. We're going to do that. So let's say that we're sizing our cooling system for 60 degrees. Good. That's what it's going to start designing everything out to. And then below that, we've got our indoor design cooling relative humidity. It's going to give you 3 options here. 45%, 50%, 55%. I will generally try to shoot for the lower end of that just because I feel that at least where we're at here on the East Coast, if we can manage that humidity inside the building, we are leaps and bounds ahead of ourselves. I'm not so much concerned with the indoor temperature in the summertime as much as I am the humidity. To have a house at 68 degrees when it's 100 degrees outside would feel cold, right? Yeah, that'd feel good. Well, maybe if the humidity's under control. What if it was 68 degrees at 80% humidity? That is not comfortable, okay? However, if it is 75 degrees in the house and it is 45% humidity, that actually is comfortable. It's way more comfortable, even being 10 degrees warmer. It's as long as we've got that humidity under control, it'll feel good. So I'm gonna put, for sake of the calculations here, I'm gonna just go ahead and put everything back to what our typical defaults would be, 70, 75, 50%. Okay, so like I said, whenever I'm doing a site visit, whenever I'm doing a load calculation, whatever it is, whether it's a commercial building, residential building, or whether I'm trying to figure out how big of a furnace I need to put in somebody's shed, the most amount of my time will be focused on windows and doors, okay? Everything else from that, it's pretty easy stuff. So that's where we're actually going to start. If you look at my spreadsheet that I have up here, you'll see that I've already got some information kind of input into this thing, and that's only just to speed this video up. All of this information here pertaining to the glass you're going to find on table 2A of your Manual J book. So let's go to 2A. Now 2A, okay, once you get into your 2A table, you're going to start looking down the left-hand side of this table, and what you will see is different types of windows, okay? So we've got single pane, we've got double pane, we've got triple pane, we've got heat absorbing glass, we've got low E glass, whatever. This is where you're going to figure out what we've got. Now, if you can remember back to our plans here, I'm going to take a look at the master bedroom, okay, that we were working in. It had that big, the larger casement window in there. It was a vinyl casement window. So let's take a look at that. Now, if we remember, it was a double pane, window assembly, and it was clear glass. Didn't have any like shading on it or anything like that. We're not going to account for the bug screen that was there. Just in the event that they take them off. Now you will find that whether it's a small apartment or even a large house, not accounting for bug screens is not going to throw your whole design out the window, okay? So even if you happen to forget bug screens, big deal. So we're not going to account for any bug screens. What we've got is, whenever I start inputting data into like this spreadsheet, some programs will automatically formulate this stuff if it is based off of the actual ACCA Manual D book, and even some of the ASHRAE manuals. But so what I put first is the actual construction code that is associated with whatever piece of component I am working with, whether it's a window, door, floor, ceiling, wall, whatever. There is a construction code associated with that, so that if at any point in time anybody needs to reference what I have calculated everything off of, they can simply go back in here, find that construction number, and know, okay, this is where we got that number. So we go down, you can see here under the generic windows and glass doors, we've got clear glass, heat absorbing glass, reflective glass. Like I said, we've got clear glass, so I'm going to go down that category there until I find what I've got. We've got single pane operable, single pane fixed, single pane with storm, and then we've got double pane operable, double pane fixed. This was a double pane operable window, okay? It's not like a sealed up window that you cannot open. This is a window that is openable. So we've got a double pane operable window. And what we're going to do now is we're going to go across that table until we find the actual type of frame construction that we are dealing with. So whether it is a aluminum frame window, wood frame, vinyl, whatever. So we've got the wood with vinyl clad, or vinyl window kind of all lumped under one column. Now you would assume that to lump all of those different construction types under one column is foolish, but for the sake of Manual J and for the sake of their speed sheet, they have done that. So we will go down and we will see that we've got a U factor and a solar heat gain coefficient associated with this window we're working. So 1D-C, we go across, we can see that there's a U factor associated with that of a 0.57. I have put that up here, the U value, U factor, whatever, of a 0.57. Now, in this speed sheet, nowhere do they account for shading coefficients, for solar heat gain coefficients, for anything like that, which again is a shortcoming of a speed sheet, okay? So we're not doing that in here, but this is something that you would take time to look at if you were doing a big project. I spend a lot of time with solar heat gain coefficients, but anyway, we're going to move forward. Now we've got all of these next 5 columns on this speed sheet here are all pertaining to the cooling heat transfer multiplier. So we have 5 columns: north, northeast, east, southeast, south, so on and so forth. So it's taking that piece of glass and associating a heat transfer multiplier to it based on the orientation that that glass faces in relation to the sun. So we are going to find all of these numbers in 3A. So if we go to 3A, you will have all these tables here. Okay, you've got a couple pages based on what the shading is on that window. So if it's got a bug screen or anything like that, if it's a skylights, we dive into those a lot. For this project, we didn't have any skylights. This is all clear glass. We're not associating any shading to them via a bug screen or anything like that. So there's no internal or external shading. Like I said in the last video, I am not going to assume that Mrs. Smith is going to have her drapes fully drawn whenever I'm doing my load calculation, because if for, I don't know, she gets a wild hair where she wants to open up her drapes, well, now that is throwing the entire design out the window. Okay, let's say that she has Venetian blinds. I am not going to assume that her Venetian blinds are always going to be drawn and that the slats are going to be set at 31 degrees. That's foolish on my behalf. I am going to assume that they're going to be open all the time. If they happen to be closed, well then great. But I'm not going to calculate for that right here unless I know 100% that there's going to be drapery over those windows all of the time. And again, why would you have a window? It makes no sense. You might as well just have put a wall right there and done away with the window altogether. So again, we're not going to assume that they have any drapery, any curtains or Venetian blinds over top of these windows. We're going to say that there's no internal shading, no external shading, clear glass for this application. So we are in table 3A. You can see now we've got 3 columns. We've got single pane, double pane, triple pane, right? Now, under the double pane column, which is right in the middle there, now you can see we have within that little table some numbers to work with. We've got our U value with, I guess a generic U value associated with all double pane windows. You're really like, getting off the path here with some of these tables. So this is where having a specific program would really come in hand, or knowing these numbers, okay? Because then you wouldn't even deal with these tables at all. You could go straight to the manufacturer's data and you could input all of that information straight to here and do away with all of these tables together. So anyway, for the sake of this speed sheet, we're going to go under this U value here, 0.56. Now we are going to look at our design cooling differential, which for this application that we are doing here, let me go back and see, we have a cooling design of 18. So we can kind of choose whether we want to do the 15 or 18 category. And I'm actually going to, well, let's do this. We're going to do one of 15 and one of 18 to see if it makes a difference on our cooling loads for this building. So I'm going to copy this one here. We're going to put it down there. 0.57. Now we're going to input the 20 degree column. So again, now we're kind of, interpolating, some numbers here, what our actual heat transfer multiplier for that specific window is going to vary, but we've only been given 2 different numbers here to work with. So we're going to choose the low and the high side. So we're looking at the 15 heat transfer multiplier category for the first one, and then the 20 for the next one. So I'm going to input all of the 20 differential information into this. So we've got our first number there, north, that's 24 for a heat transfer multiplier. The northeast would be 52. The east and west is 73. The southeast and southwest would be 63. and then the south is 38. Cool? Cool. You can see I put another window in here. It's basically the same exact thing, okay, but it says actual. That is because on my actual window, I have an actual window over here in storage that has a heating U value associated with it, 0.3. Okay, it's a really good window. So I took the 0.3 U value and then all of the numbers associated with that for our heat transfer multipliers and cooling, and we're going to just throw it in there and see what that window would do for us in terms of heating and cooling loads within this particular application. So that's the glass. Okay, if you had more than one piece of glass for your particular building, you'd put them all in here. Okay, if you had some of your windows were operable, some of them were not operable, like this building that I'm in right now, that's the situation where I have some that are totally inoperable fixed sashes. I would put that information in here. I'm not talking about like where we have locked the sash, okay, and not allowed it to operate. I'm talking about truly inoperable windows, okay. That's what we've got here. So as long as now let's just say that every single window within this building is of the same construction. You only have to put one of these construction numbers in here, and then it will automatically formulate that for every single window. So that's that. If you had any skylights, you would put them down here in this lower portion of this table. Again, we don't have any skylights here, but yeah, if at any point in time you are kind of stumped as to what maybe you should be putting in there, there is a help tab on the bottom. Okay, it's this blue help tab. You can click on that. You could click on the Read Me tab. It gives you some information as to kind of generic things about what information you should be putting into this, or on the actual tab itself, on the bottom of all of these yellow tabs, it has kind of some examples of the information you should be putting in. So if you kind of get a little stumped as to maybe something doesn't look right, go down here and it walks you through some examples as to what numbers you should expect to see in all of these boxes that you are inputting. So that's that. Once you've got all your glass in, now we can actually go to the glass schedule. Okay, it is this last green tab over here. So we've got our glass schedule. Now this is where you look at every other window in the entire building. So first things first, this is where we start taking into account the orientation of the building on the piece of property. So a lot of programs will say, what direction does the front door face? Does the front door face north? Does it face south? Does it face east or west? Whatever. That's how they kind of determine, how you're building the thing out. So here I'm actually looking at what direction does the actual piece of glass face. So for that bedroom window, we're going to click on it. Okay. This is our 1DC, which is the double pane operable window, no shade, and it is a vinyl construction. What direction does that glass face? It faces west. Where's west? There it is. Boom. So it's actually like west, southwest, but I'm just going to say that it's west here. Now we've got these next three tabs here. You'll remember whenever we were out, I told you that we needed to take a few measurements pertaining to the location of that window within the wall. Okay, so how far down the wall vertically is that window from where the soffit actually meets the top of the window? What is the depth of that soffit? So from the face of the wall out to the gutter's edge, what's that dimension? Okay, and then you need to know the actual height of the piece of glass. So is it a 3 foot, tall piece of glass, 4 foot, whatever. If you had for instance, like a sliding door, you'd put 6'8" right here, okay, for that H dimension. So the height of the opening, H, all of these are in feet. I know that one was 4 feet tall. The overhang distance, so this is from the face to the gutter. What was that dimension? That was 1.5 feet. And then from the soffit to the top of the window, what is that dimension? That dimension was 12 inches, so I'm going to put 1 foot there. Now, these next two categories are drop-down boxes, okay? Oops. If you had a bay window like I have in my office, or if you had a garden box window, which I don't see, and I think for good reason, because those things are like ovens. They just bring so much heat into the house. They are great for growing a garden in your house. And then a French door. You can specify that here. We don't have any of those for this. And then here again is where if we had a bug screen on here, we would say that we have a bug screen. I am not going to say we have one. Again, it's really not going to throw you off a whole lot on your cooling loads one way or the other. So that accounts for all of our windows that face west. Okay, so now we have, if you remember back to our blueprints, we've got two windows that face the south. One in the dining, one in the extra bedroom there. So we are going to, again, pick the same window. We are going to drop down box to the south position. The height of those windows, they were actually 3 feet. The distance to the overhang, this is on the back gable side of the house. So we are going to measure from the top of the window to where that gable is, okay? Which for both of those windows is in excess of 5 feet. But anyway, we'll put it in there because maybe around lunchtime you might get a little bit of shade on that window, where in reality you probably won't, especially considering these are facing south. If it was on the north side or maybe like the northwest side, you might see a little bit of shade on a gable end window. But for this application, I'm just going to stick it in here. The distance of that overhang is 1/2 foot. And then from the top of the window to that gable, we're going to put 5 feet here. Okay, you're going to see that the effect of shading on this window is like null and void because it's so far away from that overhang. So that is it for our glass schedule. Okay, and then you do the same thing here again for skylights if you had any skylights. So now we're done with the glass. This is great. We can move on to the doors. Again, I've already input some information here. We're going to be moving to construction code 11 in our table 4A. So once we are done with the glass, okay, now everything from here on out you're going to find in table 4A. So we're going to go to table 4A, wherever it is here in our manual deed book. Boom, there it is. Doors account for 1 page in the table 4A, so there's not a whole heck of a lot going on here with doors. If you had the information specifically to that door, like when you buy a brand new door, it's going to come with that tag on there that tells you everything that Windows tell you. You could put that in here and skip over this 1 page, but for the sake of this, again, we're going to go ahead and put it in according to the book. So we've got construction code 11N, and what does that mean? Well, if we go down and we look at 11N, this lets us know that we are working with a metal door, not a wood door, and that it is of a polystyrene core, okay? And it does not have a storm door on it. If you had a storm door, you would notify that here, and you would actually have a construction code 11O. So we go across to our polystyrene core, we give a U value of 0.35. I input that in my speed sheet up here, and we're done with doors. That's it. We're done. Okay, that's pretty cool. So yeah, if that, and again, this is this is where this specific speed sheet. Again, I don't know if it's been updated since I've downloaded this all those years ago, but what you'll see is in table 4A, they ask about the actual color of the door, so that we can, just like we did for the windows when we were trying to find our heat transfer multiplier, you will do the same thing here based on our cooling loads. Okay, so we need to know the color of the door, and so on. But for the sake of this speed sheet, they don't have any of that information here. You might have it in whatever program you are using. So we're done with doors. Let's move on to the walls, okay? Now we've got a bunch of walls to look through here. What you'll find is that most walls, in new construction anyway, are all going to be about the same, okay? Most walls are going to have like a 2x6 construction, unless it has a severe load on it to where they might have bumped it up to a 2x8. But we're going to be looking in these two pages here, Construction Code 11, and what you'll see is we've got Construction Code 11. Oh yeah, there we are. Construction Code 11. These are our above grade walls. I've put two of them in here. We've got a 2x4 and a 2x6. The 2x4 wall, I've associated an R11 insulation with no exterior board insulation, and it is a vinyl finish. So we've got vinyl siding on the outside. We don't have brick or stucco or anything like that. For my actual apartment, we are going to say that it is a 2x6 frame and that it has an R21 insulation. Now, what you'll see is if you go through here, you've got 2x4 insulation with you've got a 2x4 stud cavity with no insulation, R11, R13, R15, okay? And then you've got 2x6 with R19, R21. I don't think they go any higher than that. No. So I have opted to go with the R21 for my particular walls only because whenever I opened them up to actually put some windows in, I have determined that it is a true 2x6 stud, okay? It's not 1.5 by 5.5. It's 2 inches wide, 6 inches deep. And it's it's old sawmill wood, and it is packed with insulation. I can't remember exactly what the bats are, but there's a good bit of insulation in there. I'm gonna err on the side that it is more insulation than less, okay? And that is of your discretion whenever you have actually done your site visit as to what the overall R value is of your walls that you are working on for your project. So that's that. And then what I also found whenever I was cutting the windows in was that there is board insulation on the building. Now, whenever we bought that building, we were told by the real estate agent that there's board insulation. Whenever they redid the building in the mid to early 90s, that they had all the, before they put the vinyl siding on, they put, some nice heavy blue board on the exterior, sealed everything up, and although it wasn't a lie, it wasn't exactly the truth. It is like wafer board kind of. It's no more than like if you go to dinner and you get like that carry-out container, that foam like that styrofoam that it is made of. That's kind of what's wrapping this building. It might be a 1/4 inch or maybe 3/8 of an inch thick. So I have put that in here. I'm giving that an R value of 2. Okay, although I'd be surprised if it was that high, but I'm giving it an R value of 2. And I went across and I found an effective U value for that with the wooden studs, okay, not metal studs, but with wood studs, of a 0.06, okay. In 2021, I saw more construction projects utilizing metal studs than I have in many years, and I think a lot of it was just because the price of lumber went through the roof. So their alternatives were either concrete or metal, and I did see quite a bit of metal going in, at least where I'm at here. So you would specify that right here, because there is no better way to transfer heat from the inside to the outside than through a metal stud. So that is where you would put that information in there. Moving along, if you had any partition walls, this would be like a wall between two different apartments, or if you had, if you wanted to do a room by room calculation, or a partition between like a garage and the house, okay, like if it was an attached garage, that's where you would put your partition wall in. For this one, I'm going to pretend that that apartment is a standalone building and is not part of a bunch of other buildings or apartments. So we're not doing any partition walls for this one. And then below that, Construction Code 15, that deals with our below grade walls. So our apartment, if you remember, was sitting on top of a crawl space. That crawl space we have to account for, okay? Because we are going to be radiating heat through that floor in the wintertime, and then that heat is going to be radiating through the walls and through the floor, so we have to account for it. We've got below grade walls here, starting with construction code 15. So if we go back, these are our below grade walls. I am associating, you know, the construction with this code here, this 15A-10, meaning that we have a cinder block wall. It is not filled, okay? So these are open core blocks, and they have R10 blue board on the inside of those. So whenever you're looking at the insulation on the inside of a basement or crawl space, we need to know, does that insulation go from the sill to grade? Okay, so if you had, let's say, an 8-foot basement, okay, and the grade outside, because on our site visit we measured what that actual grade was, and let's just say that the exposed area of the foundation wall is 12 inches. Does that insulation go from the sill to the grade, so it's a 12-inch piece, or does it go from the sill to the floor? That's where we're specifying right here. So I've got R10 blue board insulation that goes from the sill all the way down to the footer, or to the finished floor of the basement. So this is my U value associated with that, a 0.056. If you had any other type of construction, you would associate that with whatever you found in the book. So that is it for our walls. Now we're going to move to our ceilings. If you can remember, whenever we did our site visit, we had two types of ceilings in this apartment. We had a traditional like flat roof that had an attic space above it, and then we had like that vaulted area or like a cathedral type of ceiling over top of the kitchen and dining with that catwalk that ran right down the middle. So we've got two different types of ceilings that we're working with here. First, okay, if we go to construction code 16, this is our ceilings under a attic space, okay? So when you're in your Manual J book, okay, there are several pages and they all look identical, okay, associated with ceilings under attics. And it's not until you actually start looking at them that you realize, no, they're not identical exactly. All of the U values associated with the assembly will be the same, okay? So our construction assembly contains a piece of 1/2-inch drywall, some fluffy insulation, and then an attic space, and then a roof assembly. So the U value of that is going to be the same regardless of whatever conditions may arise. I mean, we've got, you know, there's a U value associated with the drywall, there's a U value associated with the studs and the cavity insulation, and a U value associated with everything else. So that is going to remain the same, but what differs is what the actual temperature is of the attic space. So if you had a, let's say, a sealed attic that was unconditioned, okay, they can get really toasty hot, especially if you've got a dark like shingle roof or a metal roof with no radiant barrier. It can get very hot, and that is where the difference in all of these tables is. So our 16A construction number, which in this particular book is page 362, that first table there is associated with an attic, you know, like a ceiling under an attic, but if that attic space is 150 degrees, okay? So if you, again, didn't have a radiant barrier, okay, and you had dark shingles, and you went up there and it was 150 degrees in that attic when the outside temperature is 95, then this is the table you are looking at. Let's just say it wasn't that bad. It's 95 degrees outside and it was 120 degrees up in the attic. So if it was a vented attic to where you're getting, you know, moderate to decent airflow through it, it's going to be a little bit cooler. You know, you've got good open soffit, a nice ridge vent. It's not going to be 150 degrees up there. It might be 120 degrees. This is all part of your site visit. So this is where you're going to be looking at table 16C, all of the numbers associated with that assembly. Let's hypothetically say that you went out and you see that they've got a nice power fan up there, and when it's 95 degrees, you go up in that attic and it's 96, 97, 98 degrees. Well, there's a table for that. That's 16F, okay? So you will use all of the information given whatever U value you deemed that you had with that attic. So what I have used here was 120 degrees for my attic. So I'm looking at 16C. If you look at my speed sheet, you can see I've got 16C-13, which means that the insulation that I've got in between the cavities is an R13. Like I said, we had the beams in that attic and we had the drywall that ran underneath of it. The only thing holding that drywall up is a 2x6 stud with some insulation in it. So there's not a whole heck of a lot of insulation in there. It probably is about R13. So that is what I'm using. So we go 16C-13, we go across horizontally. We see that we have a U value of 0.07. Okay, that is what I stick in here. Now we go across and we've got our design difference in daily range. For Auburn, Alabama, we go back to our page and we see that we've got a cooling differential of 18 and a daily range of medium. So we would look at that when determining what heat transfer multiplier we would use for our ceiling. Now I used 40 because in Pennsylvania we have a 15 degree cooling design and a medium temperature range, but we could also probably bump that up to like a 45. And again, the nice thing with this spreadsheet is you could, unlike a program, if you tell a program that this is where you're working, they have numbers that they put into there. I could fudge these a little bit. The book says for a 20 degree temperature difference and a daily range of medium that we could have a 45. Let's just say that I wanted to put 43. I could put 43 in here, okay? And then it would size all of our heat transmission through that ceiling based on a cooling design temperature differential of 43. So now if we move down, we're looking at the area above the kitchen and the dining. This is called a ceiling below a roof joist. Now this, for whenever I very first started doing these, I didn't really know what that meant, a ceiling below a roof joist, until I was going through the book. I think it's like page 191 or something. But in the front of this book, it really breaks down a lot of things for you. Like if you had a question as to what a certain abbreviation was, you could find it in this book. If you didn't know what a certain construction number meant, you could find it here on page 191. That's what it is. So what this is it's actually considered a roof ceiling sandwich. And that makes sense, at least to me. It is no more than a sandwich, to where we've got a roof, and we've got a ceiling, and it's a sandwich. Easy. So that is what they mean by a ceiling below roof joist. Again, if I go over here to the construction number 18, that is where we're dealing with ceiling below roof joist. You would go down through here, you'd find your construction number based on the insulation that you know is in that cavity. I don't know, but I'm just assuming that it's probably like an R13 because it's not a lot. Then you would associate a U value, with that. I just went on a job the other day to where they had like R53 or something like that, packed into this attic space. Now there is some sort of a diminishing return once you start packing insulation on top of insulation, but for the sake of that project, that is the number I'm using to determine what the heating and cooling loads are for that building. They have a nice, and it's all sprayed closed cell foam, so that has reduced the load on that building drastically. So there we are. We did the same thing that we did with the regular ceiling under the attic with our roof sandwich. So now we're done with our ceilings. The last thing that we have to do is the floors. So if we look at our floors here, if you remember, whenever we did our site visit, we had two types of floors in our apartment. We had one floor that was of a traditional construction, 2x10, joist, some insulation, subfloor, carpet, done. Okay, that is a pretty traditional type of way of building a floor. Then we also had the grain mill floor, the original grain mill floor that was in that building from the 1800s. That is not going to be found in a program. So what I had to do is I had to first determine what the species of wood was, and then I had to determine what the average thickness of that wood, 2 inches, that's what it is. Then I could determine what the slab R value is. I could add to it the insulation value, and then I could take the inverse or the reciprocal of it and give myself a U value with that grain mill floor. I think I found it like right around a 1, like the R value is like about 1 per R, or yeah, the R is 1 R per inch, okay, for the species of wood that I'm working with on this grain mill. So we had about 2, like an R value of 2 for the actual piece of wood. I added to that 13 for the insulation that is in the cavity, and then I took the inverse of that, or the reciprocal, and I got a U factor of a 0.067. Then I applied to both of these floors, the traditional floor and the grain mill floor, our design heating differential and our design cooling differential. What you'll find is, like for over a crawl space, your cooling differentials are going to be pretty low, even when you're down south. I mean, that's why animals burrow into the ground, okay? So we have a cooling differential of 3.9 across that floor and a heating differential of 14.4. I would assume that if you were up north, you'd have a much higher differential on your flooring. Let me see here. Even then, it's not, you might get like somewhere in the 50 range on your heating differential. But anyway, and that's if you're like in Alaska. All of these are your construction number 19, okay? What it comes down to is what insulation do you have on the exterior wall, okay? So let's just say that you didn't have any insulation on that exterior wall at all. You'd be using this or the construction number 19As, okay? That's this first page with no insulation. Once you find whatever type of insulation you've got, you go U value all of these differentials and you're good to go. Again, if you remember, I have that R10 board insulation on the basement wall. So I went through here, I'm in construction number 19C. I go down, I find that I've got an R13, so I used the 11 just to be safe. Loose fill or blanket, and it is in a sealed attic, and it's not a vented attic, or crawl space. It's a sealed crawl space. So I go across, I find a U value of the floor of a 0.073, and then we go across and find our design temperature difference for the heating. Let me put that in there, 14.4. Good. So that is that. Now we have our floors, we have our ceilings, we have our walls, we've got our glass, we've got our doors. We did the glass schedule. Now what do we do? Now that we've got all of our building construction stuff actually input into the speed sheet, we can finally start putting some dimensions to it all and getting some BTUs. So we go over here to J1 form. Now you can see that it's automatically starting to populate some data for us based on what we have put into the glass schedule. So we have our double pane windows with no shade facing west and facing south, okay? So up here, again, in the top, we can start putting in our rooms. I'm going to look at my blueprints and I'm going to go around and figure out what my rooms are. So we've got a kitchen, we've got a dining room, we have bedroom 1, we have our master bedroom, we had the laundry room, and then we had our living room. Good? Okay, so that was all of our rooms. Now, let's start with the kitchen. In our kitchen, what windows do we have in our kitchen? None. We have no windows in our kitchen. Most kitchens have a window, but ours doesn't. Most windows have the window right above the kitchen sink, and it's on the exterior wall, and our kitchen sink is not even on the exterior wall, so we don't have any windows here, so that's pretty nice. Dining room, we do. We have one south-facing window, and if you remember, it was 3 feet tall, 2 feet wide. So how many square feet is that? 6. Okay, we've got 6 square feet. We're gonna hit enter, and you can see it is automatically calculating some data for us based on a southern-facing operable double-pane window. You can see our heating and cooling BTU loads associated with that window. Bedroom 1. We had the same exact thing. We had 6 square feet on that casement window. On the master bedroom, it's 32 inches wide. So what is that? We got 32 inches, 2.6 feet, and we're gonna multiply that times the 4 for the height. We got 10.6, and I think it'll round it up to 11. Yep, 11. Laundry room, no windows. Living room, no windows, and that is that. So we're done with windows. We had 3 windows in this place, you can see, and it has automatically populated some data for us as to how many BTU we're contending with there. So now we're going to move down to the doors. We're going to go down to this yellow box here, line A, and we're going to open up the drop down, and it's already going to bring us up that polystyrene door. And we're going to go to the living room tab, which is this last one, and we're going to put the information in for that. Now, you can remember it was a 6'8" door, right? Okay, 6'8", and it was 34 inches wide. So I'm going to say it's like 19, but it's like 19 and a half. So we'll say that's 20 square feet on that door there, and boom, it has automatically populated some data for that door, and our block load, okay, it's starting to add this all up. So if we go down here, you can see it's going to start adding up some block load for us. No more doors, that's it, only one door in this place. Above grade walls. So we are going to choose the 2x6. Now this is where you would look at your blueprints or your notes that you took, and you're going to start dividing rooms up. And it's easy to divide rooms whenever they are legitimate rooms. Where it becomes a little bit more difficult is whenever you've got these open concept floor plans that you have to determine, is that wall part of this room, or is it part of that room, or how do we want to chop this all up? If you can remember, whenever I was looking at that apartment, our living room, kitchen, and dining room is one big area, okay? But we have to mentally kind of chop it up into little sub-zones. One for determining what the loads are for each area, and then 2 for determining what ductwork and airflow we need in each one of these areas. So I had made it easy, and we looked at the living room, okay, and we decided to chop this one up based on where the carpeted area was, and we're calling that carpeted area the living room. The kitchen, we're going to call everything from, this kitchen area, and then obviously this little area where that window was as the dining. So it's a very small dining room, but that's how we're chopping this up. And let us take a look here. So let's start with the kitchen. So we know that this wall, okay, this exterior wall that runs here is 25 feet. I shouldn't have chopped this off of the easel. I should have left it on the easel. Okay. So this was 25 feet in this direction here. We know that our living room is 9 feet by 12 feet, so we're going to subtract from that. We're going to take 9 feet from the 25, and that's going to give us this living room area. So we're going to say that we've got 25. We're going to subtract the 9 from that. We're going to get 16. So we're looking at this wall here, 16 feet. So we have an above grade wall. Okay, so 16, and then we need to add to it the length of this wall here, right? So if we remember, this was all 19 feet. I'm going to call this living room, or this dining room, sorry, is 6 by, we'll say 6. It might be a little bit bigger than that in reality, but we're just going to say it's 6 by 6. So we've got our 19, we're going to subtract from that the 6, and that means we have a 13 wall. So we're going to take that 13 plus the 16, and we're going to get a wall length of 29 feet. We're going to take that, we're going to multiply that times the 8, and we will get a square footage of 232 feet for that kitchen. We're going to go through and do that for every single room, subtracting from it any openings like windows or doors. So let's look at this one. We have this wall section here, which is, like we just said, 6 feet times the 8 foot in height. Okay, so that gives us 48. And then we're going to subtract from it the opening of the window, which was 6. So that gives us a net area of 42. Okay, bedroom. Over here, it is 11 and 12. So we've got 23 feet there. We're going to take the 23 feet times 8. We're going to subtract from that the 6 feet for the square door, and we're going to get 176 for, or no, 178, I'm sorry. Can't see it. 178 square feet, a net area for the bedroom one on the wall. The master bedroom, 12 by 12. We would consider this a partition wall, but we're not going to. Since we're only figuring the block load, we're going to do 12 minus this area here, and then we're going to add to it the difference. So that is 12 minus the 4, that gives us 8, plus the 12 gives us 20 times 8 minus the area of this window, which was 11, 149 square feet on a net area. And then the laundry is, we're just going to call this a 4 by 4 laundry, but we're going to have 4, 4, and 4. I'm going to act as if this is like an entire room protruding from the block load of the building. So we're going to have 12 square feet there, or 12 linear feet there, and then we will take that, multiply that times the 8, we'll get 96. There is no exterior walls or anything there. Oh, I almost forgot the bathroom. I forgot to put the bathroom in the block load. So we're going to figure the bathroom, but quick, let's do this one. It's 9 feet and 12 feet. This is easy. We're going to do 9 feet plus the 12 feet. We get 21 feet. Multiply that times 8. We're going to subtract from that the area of the door, which is 20. And we get 148 for a net area there. And let's add that bathroom. Almost forgot about the bathroom because it is a small bathroom. So we have what, 5? So 5 there times the height of 8 gives us 40 square feet and some heating and cooling loads associated with that. So now we go and we get some totals here. We have a net cooling of just about 1,000 BTU per hour, and a gain of, or a heat loss of just over 2,500 BTU per hour. So that's just on our walls. Let's go down. We got below grade walls. We're going to go through, do the same thing. We're going to take the perimeter of the whole building and basically input every piece that we did here. We're just going to go ahead and copy that all down. Their ceilings. Now we're taking the area of each room, and we're going to have to divide this a little bit differently. If you had a room that was just flat ceiling, or a house that was flat ceiling the whole way across, it's easy. You just take the area of every room, boom, put it in there, you're done. We have this weird area here with this catwalk that we have to take into account. So this area is that vaulted ceiling. And one thing that we're going to have to remember is it is not the 13 feet that we're dealing with here at linear, at the linear dimension. It is 13 feet of a ceiling, but that ceiling's on a pitch, okay? So this is where knowing the pitch of the ceiling comes into account. We have to determine what this dimension is here so that we can put that into the computer, right? So we would go ahead and do that for our ceilings. 2 ceilings here. Our floors, again, remember we have 2 different types of floors. You're going to find the area of each room, split them up based on what the floor is. So we've got, you know, this big area that has the grain mill floor. The rest of the building is all a traditional style floor. And then we can start figuring out our overall BTUs. So I'm going to go ahead and put this information in here really quick. And yeah. Okay, so really quick here, I wanted you to, if you could take a note to the bedroom 1 and master. I had accidentally put the area of the ceilings under the wrong category. So, like, let's look at the master bedroom here. We're working on the ceilings. I've got one ceiling, again, that's under an attic, and the other ceiling that is that roof sandwich. I had accidentally put the 144 square feet under the roof sandwich. You can see what our heating load is of 525 feet, when in reality, it's only 484 feet, or I'm sorry, BTU per hour, because I had put it in the wrong category. So make sure that you're putting it all in the right category. And again, bedroom 1, we would have oversized our heating and cooling equipment by a whopping 200, or I'm sorry, by a whopping 20 BTU had we not caught this. So make sure that you're putting it all in the right category. Alright, so now I have finally got all my dimensions into the program here pertaining to all the windows, floors, doors, ceilings, and everything like that. So now we are going to look at our envelope leakage. Now this is where some softwares will allow you to put in a blower door number. If you had a blower door test done on your building, you can put that information here. Here, you can't do that. You're using your own discretion as to what you think the envelope leakage is. So I am going to say that this is probably pretty average. If anything, it might be semi-loose, maybe. I don't know. It's not that bad. But again, I think they might specify as to how many air changes per hour your infiltration might be based on these generic terms like tight, semi-tight, loose, and everything like that. Let me see if they do. Yes. So on table 5A, this is page 196, they will tell you what, based on what you're calling your construction, how many air changes per hour that means. So for an average building that is 900 or less square feet, that gives you an air change of 0.61, okay? As your building gets bigger and bigger and bigger, your air change volume must remain lower and lower to give you that average notation, okay? So like if you had a building that was 2,000 square feet, for it to be average, you'd have to have air changes to be a 0.38, okay, per hour. So, and that's for heating, and then for cooling, that same building at 0.2. So, yeah, I mean, again, use your discretion. Take a look at this 5A table, and you can determine what your building is. Is it average? Is it super tight? Is it loose? Whatever. So I'm gonna say that this is an average construction, you know, for our infiltration anyway. So anyway, moving forward, we've got our heating and cooled square feet, our floor area. So you'd simply just take your dimensions of your building, which for us it's 25 by 30. It gives us 750 square feet. Then we take our above grade cubic feet, which is just that, our above grade cubic feet. So we can take that, we'll multiply that times, we'll say 10, and give us 7,500. That's just, I'm just totally guessing there. I'm not actually even going through the math of measuring all that out. So now we're going to put in here the number of bedrooms we have in our house. And what you'll find is, based on the number of bedrooms, like I said in my last video, it kind of will then populate an idea of how many people are in here, how many occupants we actually have. So for a 2-bedroom house, it's going to say that we have 3 occupants. So it's going to take 1 over the amount of bedrooms. Now what we have to do, we have to assign each one of those occupants to a bedroom. So I'm going to put, let's see, 1 in each bed. Yeah, 1 in each bedroom. We've got 1 here. We're going to put 1 in here, and then I'm going to put another guy in the kitchen just because, why not? So now we have 3 people in this building, giving us a cooling load of about 700 BTU per hour just for people being in there and sleeping and eating and everything like that. If you were doing your manual N and you were looking at a commercial building, this is right here where you'd have to assign what these people are actually doing. Are they in an office situation to where you'd have a similar BTU output of that, or are they on a treadmill? Okay, is it a gym to where we're sizing, 3 people running on a treadmill is going to put out way more cooling load than 700 BTU per hour. So, but we're not doing a manual N, so we're not going to worry about that. Now we've got appliances. Appliances, we're going to start chopping up here. I'm going to err on the side of caution and say that we got, excess appliance. And the reason I'm doing that, not because we've got a big commercial kitchen and a deep fryer and everything that you might think. The reason I'm adding BTU on our appliance load is because it is becoming more and more popular for homes to become offices, and because of that we have more computers, we have obviously TVs. I have just this one monitor that I have right here. I can feel the heat just resonating off of that thing. So what I'm going to do is I'm not actually going to put all of this appliance load into the kitchen. I'm going to divvy it out between the bedrooms as well. So I'm going to stick in the kitchen, we'll say 1200 BTU. I'm going to give the bedroom 1 600, and then I'm going to give the master bedroom 600, and it's going to give us an overall cooling BTU load of 2400. And now we are accounting for each one of those in the bedrooms. I was called out to a customer just 2 days ago that we had put a system in this house probably 2 years ago. And they said that they're having one room that they're having an issue with. And, well, come on now, I did this, so let's figure out why. I went out to the house that they're living in now, and what they ended up doing was the one bedroom all the way in the back that they're not using, they turned into not only an office, but a gaming lounge. You should have seen the computers that they had in this room. They had 3 of these big CPUs that were, not even kidding you, probably 20 inches wide. They were tall. They had some sort of a water cooling contraption in there to keep them from overheating while they're doing their gaming. I don't know anything about it, but all I know is whenever I went in there with the thermal camera, these things were just emitting so much heat that the register we put in that room was never going to effectively cool. So what we're we're gonna have to go back out and modify the system to allow for more air to go into that room to account for the fact that we've got all this BTU load based on these gaming computers. So keep that in mind when you're looking at houses, bedrooms, and even office spaces or whatever. So we've put in our appliance loads. Now we're gonna start getting some subtotals. Well, you can see here our subtotal for cooling is just shy of 8,000 BTU, that's low. I mean, that's pretty low, but remember, this is a very small apartment. So we've got 8,000 BTU there. Let's account for our duct losses and gains. I'm going to say, where are we putting our ductwork at? If we want to put our ducts in a conditioned space, it's going to take away any, gains or losses because they're all in conditioned area. If our supplies and returns are, let's see, in an unconditioned crawl space, here we go, okay? We're going to associate some losses and gains with that. So, yeah, that's that. All of my ductwork here is in a conditioned area, so we are going to put that our ducts are in conditioned areas. If they weren't in conditioned areas, like let's say we were in an unconditioned crawl space, and we had R2 for insulation on that, okay, and if you had sheet metal, it'd be nothing, but they don't even give you that option here. Then you can see what your BTU heat losses and gains are through the ductwork. Then we have our leakage classes that, like, let's just say we had super leaky ductwork. You can see how much BTU movement we're getting through that, or losses out of that ductwork. So we got to account for all that if it's unsealed ductwork. So yeah, if we had super tight ductwork, you can see where we're at there. Again, we are in conditioned space, so none of it matters. Even if it was leaky. So, even if you had leaky ductwork, it's just leaking into the area that you're cooling, so that's all right. If you had anywhere that you were pulling combustion air for a furnace, so like let's say you had a 90% furnace and you are drawing combustion air from a mechanical room, for instance, that's internal to the house, we need to account for that here. If you have a water heater doing the same thing, if it's atmospheric venting, this is a big one, okay, because it's drawing air from your house to get that stack effect created in the chimney. So we would want to account for that here. I do not have anything like that here, so we're not going to account for it. And then finally, what do we have for internal gains for the, do we have plants in the house, okay? Do we have a small plant, that is letting off some moisture? You would account for that there. And that's that. Now what we can do is we can go to our summary and we can see all of our heating and cooling loads room by room and the CFM associated with each one of those for both heating and cooling. What it's going to do over on the far right is it's going to take the larger of those two numbers, and that's what we're going to use for doing our manual D when we're actually sizing the ductwork for each one of those rooms. So you can see like our kitchen has the largest load to it. We need 174 CFM going to the kitchen to counteract the loads that are associated with that kitchen. And then we can see through all of our actual construction areas where we're losing all of our heat or picking up all of our heat. So that is that. You can print that out and you've got a little report there. Now, you can, this again, we're just walking through the example of that apartment. To do this all, I don't think I would use these numbers here per se. This gets you a pretty close ballpark when we're looking at a specific building. But would I use these numbers? I don't know. The biggest problem is we're not going to be able to do a manual S and find a piece of equipment that is going to give us 7,800 BTU cooling, unless we're doing like a mini split that it would have to be like an inverter mini split that on the high stage can do like 15,000, and the low side we could do 7,000 or 8,000 for cooling. So yeah, that's pretty much the only thing that manual S would allow for this building. But again, that's based on the little bit of information that manual J will allow for, So if you had actual construction numbers and data sheets for your construction material, then you could use those exacts. You could get exact numbers and you could actually figure out what needs to be done here. But again, this gives you just the process of doing it, and you can take it for what it's worth. If you wanted to use something like this, you could. Now, let's do something fun. Let's take this building. We're going to pick it up, and we are going to, we are in Auburn, Alabama. Let's pick it up and move to Alaska and see what happens in Anchorage with this same building. Remember what our loads were before. Our air conditioning hasn't changed much, but you can see our heating has gone way up. 22,000 BTU. 22,000 BTU is what we need on the heating side for this little tiny apartment. Now, what's 22,000? I mean, it's still nothing. I mean, you could do it with a kerosene heater, really. Yeah, that's taking that same building and moving it to Anchorage. We could do it again where, let's just say we went to, where's somewhere nice and warm? How about Florida? Or no, let's go to Arizona. Arizona, that seems pretty warm. Phoenix, there we go. Let's try Phoenix, Arizona. Let's see what our summary is. 9,000 for heating, 9,000 for cooling. Boom, that's a heat pump right there. So, yep, that's that. All right, guys, that will pretty much wrap this one up. Next time, we're going to take those numbers and we're going to actually dive into the ductwork. What are we doing with the ductwork? Now, like I said, these are pretty small, but we can still take the numbers and get a theoretical example with them. So, I will see you next time. Take care. Bye.